Alright, I'm no longer in a hotel, so that's nice. There won't be like planes flying over every 5 minutes. But what I wanted to do today is I wanted to start out with a theorem, or I guess I'm going to call this a corollary. It's sort of a corollary to Theorem 1.6.9 in the textbook. I think this result is actually like a direct result of that theorem, but I also want to prove this in a way that's a little more clear than in that theorem, because the proof in the book is very measure theoretic, which is good, but it makes it difficult for computations. At least from where I am at right now with my understanding of measure theory, it doesn't really give me a way to, or it's not entirely clear to me how to apply the theorem easily to aid in computations. And so just as an example, here is a fact which I think follows directly from that theorem, but I'll actually state it in a way that shows you how to do computations and prove it in a way that doesn't use any measure theory. So, and this is something that, the reason I think it's a direct corollary of Theorem 1.6.9 is that this is a fact that is used in some of the examples immediately preceding Theorem 1.6.9, but it's never really addressed. Okay. So let's say we have a distribution f, which is invertible and continuously differentiable, and it has a density function f, meaning that capital F of x is equal to the integral from negative infinity to x of lowercase f of y dy. And if x, so we have this distribution f, and we want it to be the distribution of some random variable. So we're going to let x be this random variable which has distribution f. So x is a random variable, and we're going to use the we're going to obtain a random variable from our distribution in the way outlined in the theorem that states that every function f which satisfies the properties of a distribution, meaning you go to minus infinity and it's 0, you go to positive infinity it's 1, it's monotone increasing, and I think that's it. Oh, no, it has to be right continuous? Yeah. Anyways, if x is a random variable on, and so we define this random variable on 0, 1 with the standard measure, and it's given by x of omega, where omega is some number between 0 and 1. This is a supremum over all y, such that f of y is strictly less than omega. Now, this is the definition that you have to use for general capital F, because f does not need to be continuous or invertible. But here, for this theorem, we are assuming that f is invertible. And so, since it's invertible and continuous, basically, here's what I want to do. I want to write this, f inverse of omega. And then we have, okay, so f inverse of omega needs to be this set, and so first of all, f needs to be invertible for the right-hand side to even make sense, and in order for this equality to hold, I think it does need to be continuous. Because if you have a jump, then that's where this gets sort of thrown off. But if you have a jump, Right, you could have a jump and the function still be continuously differentiable. So we don't just need it to be, so I'm going to write f is invertible and continuously differentiable. So f is continuous, f is invertible, and the derivative of f is both differentiable and continuous. And actually, well, to say that f is continuously differentiable means that the derivative of f exists and is continuous. But by the definition of the density function lowercase f, the derivative of capital F is just lowercase f. And so I guess all this is saying is that lowercase f needs to be continuous. Okay, but here's where we're going at. We want to compute the expected value of x to the k, because this is how we find the kth moment of x, this random variable. And we can compute it in this way. We take the integral, and we go from f inverse of 0 to f inverse of 1, y to the k times f of y dy. Because this is a thing that you see in a lot of those examples. Like, they show you how they compute the moments of, like, for example, the standard distribution, or Gaussian, whatever you want to call it. And they just use this fact that instead of, that to find you're basically integrating x to the k. And to do that, that's the same thing as taking this y to the k and multiplying it by the density function. And it's not clear why you're able to do this. So that's what I want to go through and prove. So let's prove this. So we're going to use a u substitution. Well, not a u. We're going to use the typical like Calc 1 type of substitutions that you use for integrals. So it's going to be y equals f inverse of omega. And so then we differentiate both sides. We get dy is going to be f inverse prime of omega d omega. And now, so why do we need continuous differentiability? We need continuous differentiability of capital F because we're going to use the inverse function theorem. And this is something from Baby Rudin. You can go read it. It's actually a very important, well, actually it's even in Spivak. But it's a very important theorem in calculus. It's, in my experience, it's not really talked about in calculus classes, but it's talked about when you take a rigorous course in calculus, like something like Baby Rudin, or something like Spivak. Okay, so, and of course by Spivak I mean calculus on manifolds. I guess not, of course, if you don't know that then it's not obvious, but anyways. So, by the inverse function theorem, what if we, so the reason that we're using this, okay, so here, let me do it first. So this f inverse prime, basically inverse function theorem tells you what to do with this, how to take the derivative of an inverse. It ends up being, let's see here, so you have f prime of f inverse of omega, and this is all on the denominator. So it's 1 over f prime of f inverse of omega. So, what does this give us? So what this tells us is that if we take f inverse prime of omega and we take its inverse, so we're just taking this equality that we have up here and we're taking the inverse of it. And so, let's see here. So I guess there is some other there might be some other conditions that we need on capital F, like you got to be able to invert this and everything. But yeah, so there might be some conditions that I'm leaving out here on capital F and lowercase f. But in any case, I'm just going to go through and continue the proof as if everything works out nicely. Alright, so we take its inverse and we get, so we're just taking the inverse of the equation that we have up here. So we get f inverse, we get f prime of f inverse of omega. Therefore, we have... Okay, so why did I do this? I did this because we have this dy equals f inverse prime omega d omega. And what we want is we want the d omega by itself, because that's what we're going to be removing when we do the substitution. And so we have d omega is equal to f inverse prime omega dy. And we want to know how to deal with f inverse prime. And no. We get d omega equals 1 over f inverse prime omega dy. And so we want to know how to deal with 1 over f inverse prime omega. And it turns out it's just like this. We get 1 over f inverse prime omega is f prime of f inverse of omega. So that works out nicely. So now, let's see here. Let's do this. Okay, so now we want to compute the expected value of x to the k. Remember, by definition, this is just the integral from 0 to 1, because that's the domain that x lives on. X to the k of omega. We're integrating with respect to omega. Alright, so we have x to the k. Remember, x of omega equals f inverse of omega. So this is simply integral from 0 to 1 of f inverse of omega to the power of k d omega. And now we can do our substitution. So we're going to replace f inverse of omega with y. So let's see, with the bounds of the integral, when omega is 0 or 1, then y is going to be f inverse of 0 or f inverse of 1. So we have f inverse 0 and f inverse 1. So we have this integral, and now this f inverse omega to the k, that's just going to become y to the k. So that's where that comes from. But now we gotta figure out how we get this lowercase f of y. Well, remember, d omega is, as I was saying, this is going to be f inverse prime omega 1 over this dy. Because that's just what we have. You take this equation for dy and move the one thing over to the other side, and so we get this. And so then, well, we've figured out how to deal with this thing. So this is going to be f inverse 0 to f inverse 1. Now we've got y to the k. And now this part is going to become f prime of f inverse omega dy. But now we know how to deal with this. Because we're just using our substitution. F prime of f inverse omega. Well, f inverse omega is just y. So this is f prime of y dy. But remember, f has distribution or density function lowercase f. And so that tells us that we can actually replace f prime of y with lowercase f of y. And that's what we were trying to prove. We were trying to figure out how we get from the expected value of the random variable to an integral involving the density function. And this is how you do it. And now that we understand why this works, we can use this in later theorems and exercises.